Hi everyone, I'm Suprita Bhaumik and welcome to week 9 of live session for the course Fluid Dynamics for Astrophysics. We'll first revise the material that was covered this week and then we'll move on to sample assignment problems. So this week we covered spherical blast waves and also a little bit of MHD induction equation. So first let's revise um, what these spherical blast waves are. So one of the important astrophysical contexts of spherical blast waves is, of course, supernovae. These are essentially a result of a large amount of energy deposition, and it's assumed that this large amount of energy is deposited at a point, and then once this energy is transferred to shock waves, it propagates out. These shock waves propagate out in a spherically symmetric manner, and these are assumed to be self-similar profiles. Self-similar profiles in the sense that at different times, these shells, these shock shells, are basically have the same profile. They're just scaled versions at different times. All right. Uh, and then it was discussed what essentially supernovae are, since this is one of the astrophysical context of spherical blast waves. So to discuss that, we'll just revise what was discussed in the lectures. So where do supernovae come from? What essentially are supernovae? For that, we'll have to delve a little bit into stars, their main sequence phase, which involves the um, phase of the star which burns hydrogen into helium, and then how stars, when stars ultimately die, what happens. So, in the main sequence of the stars, this is the phase of the star when the stars will burn hydrogen into helium, and the energy that is released from these reactions uh, is what exerts the outward pressure, keeping the star from collapsing onto itself due to its gravitational pull, right? Uh, but as the star keeps burning hydrogen, it will eventually run out of hydrogen. It will eventually run out of fuel to burn. And when that happens, there's not enough outward pressure coming from, because there are no reactions going on. And what can happen then is that the gravitational pull of these massive objects will result in core collapse. But this happens for very heavy stars. How heavy? Which are much larger than solar masses. So let's say much larger than 8 solar masses, right? That will result in neutron stars. And if you go to order 20 solar masses, that will result in core collapse to form a black hole. Okay. But what happens to stars which are, let's say, comparable to the mass of our sun? When stars of solar mass die, what essentially means by death is that the hydrogen in the core of these stars is burnt out. What the stars then does is, it's not heavy enough for core collapse. What it starts doing is it starts burning hydrogen in the layers outside of the solar core. Okay. And what this results in is an outward pressure. Okay. And this outward pressure will dominate the gravitational pull of the star. Okay. This results in the star being blown up to a red giant. These are colloquial terms you must have heard. Okay. And these objects are quite unstable. So what can happen is a stellar wind can blow off these outer layers that have blown to really large red-eye, and these layers are blown off as planetary nebulae. What is left behind is the core, where no longer thermonuclear reactions are taking place, which is the white dwarf. Okay. Now these white dwarfs are very compact. These are very heavy objects. How compact? So let's say if the sun uh, did die at some point, which it will. If the mass of the sun were uh, if the sun were squeezed to proportions of, let's say, the earth, so these are very compact, very heavy remnants of a star, and these are composed of cores of heavy material, carbon, oxygen. There are sometimes thin layers of helium and hydrogen around these cores, huh? and these are white dwarfs in the sense as there's no energy production, there's no thermonuclear reaction taking place in the core. Okay? Now, sometimes what will happen is these white dwarfs will find a companion and they start creating material from this companion. Okay. So what this does is it starts accreting material and starts gaining mass. This accreted material will start imparting some gravitational pressure on this core, right? What this will do is, due to such high gravitational pressures, the core will start getting heated up. Okay. And once the core reaches temperatures high enough, thermonuclear reactions can start taking place in the core. Okay. This is all due to material being accreted from a companion that this white dwarf has found. Hmm? And this gravitational pressure is increasing the temperature of the core, and that results in, once again, carbon fusion. This is a runaway process. This does not stop. Why does this not stop? Why is it a runaway process? Because typically in stars, what happens is, when due to some reason the temperature of the when the temperature of the star increases, the star can expand, cool down until gravitational pressure can once again stabilize, and stability is once again reached. Okay, so when the temperature increases, the star will expand, cool down, and stabilize until the gravitational pressure can match the pressure of this thermonuclear pressure. This is how a star will stabilize. Okay, but in white dwarfs, it is not the energy from these thermonuclear reactions that is the dominant pressure against gravity. That's not what's supporting gravitational collapse in white dwarfs. What supports gravitational collapse, or what stops the white dwarf from squeezing further? It is electron degeneracy pressure. Okay, so even when the material is being accreted onto the white dwarf, and carbon fusion has started in the core, even then the dominant pressure against gravitational pull is electron degeneracy pressure. Okay, so, and one more thing is that this electron degeneracy pressure is independent of temperature. So when that happens, the white dwarfs cannot expand. They don't have any means of cooling down. Okay, so they stay that way until the temperature increases, and at some point it's too late, and then a blast happens. At that point, this the thermonuclear pressure released from due to the energy released from this carbon fusion in the core will, of course, be dominant than the electron degeneracy pressure. And at that point, the temperature has risen so high that it's a thermal runaway process, and it's too late for the star. And gravitational pull cannot keep the star in place, and it blows up. I should not say star, not star, the white dwarf. The white dwarf blows up, okay? And it blows up into a supernova.
I mean, can you just say why it actually why the explosion happens?
Yes, the explosion happens because this carbon fusion is then a runaway process, okay? This keeps on, the temperature keeps on increasing.
Okay,
There's no way for the star to cool down. So you see,
okay,
a lot of energy is being produced in the core, but this has no way of getting released, okay?
okay,
So gravity will keep containing it until it's too late and the temperature has risen so high and there's so much energy into the core that it explodes into a blast.
okay,
This is the same as uh, um the way we assume that the way these spherical blast waves are being formed is by large energy deposition at a point. What are these large energy depositions? We say that, okay, material is being accreted onto the white dwarf from a companion. Hmm? And then what this gets converted to is basically these this energy from carbon fusion. And temperature rises so high because there's no way for the white dwarf to cool down by expansion that it explodes as a supernova. Okay, all right. Uh, okay, then we go on to spherical blast waves and shock conditions. So we said that these spherical blast waves will arise as a result of injection of some amount of energy into a point in a medium whose density is rho 1, pressure is P1. Hmm? And we said that this is released into blast shocks, and we assume that this energy is not dissipated with time. Okay, so the way this energy would be dissipated is if these shocks waves were to accelerate the particles through the particles in the medium through which it passes. Huh? And then there'll be radiation losses involved if the particles were charged. But we say that, okay, this energy is not being dissipated. It's one of the assumptions. Okay, so we assume that this energy remains constant with time. And we also assume that these spherical blast waves are self-similar. So if at some point of time t0, the radius of the blast wave is r0, the radius of the blast shell is r0, then at time t, it will just be a factor, a scale lambda multiplied to r0. Okay, this is what means that these shocks are self-similar, that at different instances of time, these shells are just scaled versions of each other. And what is the scale? The scale is this lambda. Okay, now this is a length scale, right? Now, of course, it's dimensionless. Now, the claim is that using the relevant quantities, the relevant scales in the problem, the energy that is being uh, thrown out as shock waves at a certain time t and a density ρ1, using these relevant scales, this is the combination you can come up with to form this quantity lambda. And it works really well because it matches very well with the uh, observations. What observations? Let me tell you. So let's say we construct a dimensionless similarity variable zeta. There is a similarity variable in the sense that, and you can see that this will label blast shell. This will label a shock shell because this is like some R0 T0, right? So zeta marks a certain shock shell, and after a certain time t, this will turn into RT divided by lambda. This will turn into RT. And what is the relation between RT and zeta? It's given by this. Hmm? So a dimensionless similarity variable zeta given by RT by lambda, right? Then, and you know what lambda is, you've constructed lambda out of ET and rho. Then RT is given in terms of zeta, E, T, and rho as this. And you can see that the radius of a shock shell goes as T to the power of 2 by 5. So if you plot log R versus log T, and this was one of the graphs that was shown, this was from one of the nuclear tests in 1945. Uh, the radius of the shock shell with respect to time was plotted, the log of R with log of T, and you saw that this agrees very well with theta. So this construction of the scale works very well. Now, you can differentiate this with respect to time and you will get the velocity of the shock, and you see that the velocity goes as 1 by t. So the velocity as the shell expands, the shock slows down. The shell slows down. Okay. Now we'll prove a few conditions that were left as exercise in the lectures. So let's say 1 denotes pre-shock conditions. So if this is the shock front, right? Then in the frame of the shock front, fluid in the pre-shocked region, in the unshocked region, will move towards the shock front with velocity u1, and fluid over here, which has already been shocked, which is in the post-shock region, will move away from the shock front with the velocity u2. Okay, so the label 1 denotes pre-shocked fluid, the unshocked fluid, and label 2 will denote post-shock fluid or the shocked fluid. Okay. Now we have to prove that u2 by u shock is 2 by gamma plus 1, where u2 over here is the velocity in the shocked fluid in the lap frame. In the lap frame, not in the shock frame. Now, if you remember, we derived jump conditions being the conditions, the ratios of density, uh, pressure, and velocity of the fluid. In the pre and the post shock regions, these ratios as a function of gamma of the gas, gamma of the fluid, and Mach number. And if you remember in the shock frame, these jump conditions, one of these jump conditions with this rho2 by rho1, density in the post shock region by the density in the pre shock region is equals to this. And now we assume that we are working with an infinitely strong shock. And if you remember that an infinitely strong shock is taken as any Mach number greater than 4, because these ratios will asymptote to a constant for Machs greater than 4. And if you do this, you will see that rho 2 by rho 1 is gamma plus 1 by gamma minus 1 is the same as u1 by u2, because rho 1 u1 is rho 2 v2 by mass continuity equation. All right. Uh, Now, in the shock frame, fluid moves towards the shock front with u1, and fluid moves away from the shock front with velocity u2. So in the lab frame, actually, the velocity of the shock front is actually u1, because this is the shock front that is moving towards this fluid with velocity u1. So in the lab frame, u shock is actually u1. And what is u2? u2 is going to be negative of u2 minus u1. Is this understood? I'm just doing a frame transformation. So I'm moving from the frame of the shock to okay, thank you. So I'm moving from the stream of the shock to a frame where the shock will move with velocity u1. So I'll have to subtract this from u1, but there's a change in direction of u2 because this is essentially in this direction. So I put a minus sign and I get this velocity. Okay. Uh, all right. So if u2 is this, if I'm calling this as my new u2, then I pull out a u1 common from here, and I use this jump condition, which will tell me that u2 is gamma minus 1 times u1 divided by gamma plus 1. And I pull out a u1 as common. So u2 in my lab frame is twice u1 by gamma plus 1. But what is u1 in my lab frame? u1 is u shock. So I get u2 divided by u1 is 2 by gamma plus 1. Hence proved. Alright. Next I'll have to prove that the pressure in the post-shock region is related to rho 1 and u shock by this relation. Okay. Now, if you remember, we derived the jump conditions in the shock frame. P2 by P1 was given by this. Okay. So what I do is I pull P1 to the right hand side as this. Then I will substitute P1 with rho 1 CS1 square by gamma. Why is that? Because del P del rho is gamma P by rho is CS square, the speed of sound, right? So P I can substitute with rho CS square by gamma, rho CS square by gamma. So P2 becomes this. Okay. Now CS square I can rewrite as u1 square by Mach square, because Mach, remember, was defined with respect to the velocity of fluid in the pre-shock region divided by the speed of sound in the pre-shock region. So this was what Mach was defined as, and I can substitute for CS square as u1 square by Mach square. Okay, so P2 becomes this. Then what I'll do is I'll take this Mach square inside this third bracket. So then this becomes rho 1 by gamma u1 square 2 gamma by gamma plus 1 1 minus 1 by Mach square plus 1 by Mach square. But now I'm dealing with an infinitely strong shock. So I can drop 1 by Mach square terms. If I drop these terms, I'll be left with a 2 gamma by gamma plus 1. What does that give me? That gives me twice by gamma plus 1 rho 1 u1 square. But u1 square in shock frame is u shock square in lab frame. So in lab frame, I get this. Okay. And this is exactly what I wanted to prove. P2 is twice by gamma plus 1 u shock square times rho 1. Okay. Any questions? Okay. So then what we wanted to do was, if you remember in the lectures, a picture of a supernova was shown to you, and then we wanted to, and the supernova picture was very pretty. It was um, hints of blue inside, and then there was shades of yellow and red all around, and it was told that this regions of red is probably it's expected that that is the position of the shock front. The shock front has already passed through and shocked the fluid in this region, and it is currently at this position and is propagating outwards as a spherical blast wave, right? And we wanted to um study the variation of, let's say, the density, the velocity, and the pressure in the shocked gas, right? So we have to look at the mass, the momentum, and the energy conservation equations. But we choose to do that with dimensionless variables because that will make things easier for us. So what do? We define a dimensionless variable rho prime. And how do we define it? We define it as rho divided by some rho 2. Okay, this is some normalization variable. This is some density in the shocked fluid. Okay, and this is of course related to the density in the unshocked fluid via this because we just derived the jump conditions. Hmm? Similarly, one can define a dimensionless velocity and a dimensionless pressure. Now, to show that URT is defined as U2 by R shock times R times U prime, the dimensionless velocity, is the same as uh, this thing. What do we have to do? So R shock is actually this. If you remember, R shock was zeta times some lambda, and lambda was this. To derive the velocity of the shock, you differentiate this with respect to time, and what do you get? You get 2 by 5 times zeta times this entire thing. Is this clear? Okay, let me just okay. So R shock is Et square by rho 1 to the power of 1 by 5. You differentiate this once with respect to time. What do you get? R prime is E by rho 1, 1 by 5, um, and then 2 by 5, t to the power of 2 by 5 minus 1. So what is this? This is theta. You pull out this t to the power of minus 1 over here. You write this over here. And Et by rho 1 whole to the power of 1 by 5 times 2 by 5. Okay. So what is this? This is 2 by 5. This entire thing is R shock. So R shock divided by T. This. Okay. All right. Uh, so if that's the case, I will substitute for R shock with V shock, and I will get URT is U2 by R, U2 times R divided by R shock, which I substitute with 5t times V shock by U, 5t times V shock by 2 times U prime, the dimensionless velocity, right? So then I have a U2 by U shock. This V shock is essentially the shock velocity, which is U shock. But I have the jump condition for this. I substitute this with 2 by gamma plus 1, which is U2 by U shock, and I get this. Okay. Similarly, one can also show that P, if I define it with respect to the pressure in the post-shock region, in the shocked fluid, then I can relate it to R and T via this. Once again, I will substitute for R shock, right? So R shock was 5t by 2 times V shock. I take a square of that to get 25 u shock square divided by 4, right? With a p2r square, with a p2r square, and of course a t square because this t goes over here. So there's a t square in the denominator times the dimensionless pressure. We combine everything to get this. All right. Now, what is the point of doing all of this? So, what we have done is we have related these dimensionful density, velocity, and pressure to the dimensionless quantities rho prime, u prime, and p prime, and they're all functions of zeta. Okay. So we look at the conservation equations and we see that these are partial differential equations. These are coupled. So rho will arise in expressions for p, u will arise in expressions for p, and so on. So these quantities, these equations are coupled and they're partial differential equations. But in language of zeta, if you look at what the partial derivative, the partial time derivative is in terms of zeta, you can use the chain rule and see that del del t of zeta times dd zeta is del del t, and del t of zeta is nothing but minus 2 by 5t zeta times d zeta. Similarly, the partial radial derivative will turn into zeta by r times total derivative of zeta. So these partial differential equations turn into ordinary differential equations when written in terms of similarity variable. And then what you can do is you can use these relations and express everything in terms of functions of zeta and rewrite these equations in terms of ordinary differential equations in the similarity variable. Okay. Now the derivation is the algebra is not terribly important. That's why we're not going to derive this here. But the point is, then you can write down these equations in the variable zeta, and then you can plot solutions. You can figure out what these are, the solutions of these are, and that will tell you how the density, velocity, and pressure. What is the density, velocity, and pressure profile in the shocked fluid? So remember, these are not jump conditions that we're deriving. This is the profile of the pressure, density, and velocity in the shocked fluid. How does it vary as you move away from the shock front towards the shock fluid, towards the origin of, let's say, the blast? Okay, and that will be required in answering one of the questions in the assignment problem. So we'll look at the plot of the solution of of these equations. Okay. All right. Uh, so this was all about spherical blast waves. Then we moved on to magnetohydrodynamics. What is magnetohydrodynamics? It's hydrodynamics. It's fluid dynamics. But now you have to take care of magnetic fields because now we're dealing with fluid that is uh, immersed in magnetic fields. Okay. So now we are no longer dealing with um, situations where we don't have to worry about E and B fields. Now we have to um, see how the fluid moves, or what is the dynamics of the magnetic field given a certain flow for the fluid. Okay, all right. Uh, so once again, this is fluid treatment. So whatever arguments we gave for the continuum uh, continuum treatment, what are the limits, what is the continuum limit, and or all the approximations that should hold, and what are the limitations of this limit. All of that holds true. All of those discussions hold true for MHD, right? So remember, these are fluid treatments. We are not going to go in. We're not working with the particle picture. So there's no question of asking what are the particle orbits in B fields. Of course, we know that how a charged particle will behave in B fields, right? So it will, if it has a velocity component that is parallel to the B field, it will gyrate and move along the magnetic field. And so it becomes it loops around the magnetic field and it gyrates, right? The radius of the gyration being rg. But we are going to work on scales which is much larger than uh, than these particle orbits. So we are working in scales where these Lama radius, this gyration radius, is very small. what do you want to know about magnetic fields?
Yes, ma'am, you're talking about the fluid dynamics immersed in the B fields.
Hmm.
I would actually like to know what exactly you mean by B field. Very short, just to know the context of the whole
So the
problem.
context is the context is up until now we have just been dealing with, let's say, the equation of motion of the fluid, the mass conservation, momentum conservation, and the energy conservation. But we did not take into account any sort of B fields, right? So, for example, we studied about solar winds, right? We studied about these stellar winds, the solar winds that are being emitted from the sun. Hmm? Now, we did not take into account that there are magnetic fields in these solar winds. These solar winds carry magnetic fields. So now we have to incorporate that in our treatment.
But ma'am, then in our equations there will be added parameters as well. Then
What parameters? Come again, sorry.
actually, if we are using the magnetic field till now, we have not used. So if we are using now, then our equations might also change, right?
The equations will change
So
and we'll study how the equations change. Sure.
thank you, ma'am.
Yeah. Okay. So this is just, we are now going to derive equations of fluid dynamics, but in the presence of magnetic fields, right? So for example, we know how to incorporate body forces. We know what the body force term looks like in the equation of motion when we're writing down the fluid dynamics, right? We know how a pressure gradient term will look like, let's say. We know how a viscous term will look like. Now we want to incorporate magnetic fields and find out what is how will the equation of motion change, right? Or what is, let's say, how will the magnetic fields behave in response to a certain flow? That's what we want to find out. We not only want to find out the fluid dynamics, we also want to know how will the magnetic fields, what is the dynamics of the magnetic field? Will the magnetic field grow? Will it decay? What will happen to it? As a fluid or with a certain flow profile um, washes over this region of magnetic field. Will it carry the magnetic field? Will the magnetic field decay? What will happen to it? That's what we want to find out. Okay. All right. So we've established that we're not working with not working at scales where we can distinguish particle orbits. We're working on a much coarser scale where these gyration radius goes to zero. So um, just to review, what happens is if you have a charged particle, since uh, this might be new for somebody who's not from physics background. So if you have a charged particle and you have a magnetic field, the force on the charged particle of charge q moving with the velocity v is given by the cross product of the velocity of the particle with the magnetic field. This is the force acting on this charge, right? So what that will tell you is the particle will actually move like this, right? Uh, but if we are working in the fluid picture, we can't make out different particles, right? So we have to work on much coarser scales where we cannot make out these scales because these are very, very small. So this will go to zero on scales that we are working with. Hmm? We can't make out this motion of particles because we can't make out particles. We are working in continuum limit. All right. Also, these are all charges, of course. Because fluid that does not have any charged particles, of course, will completely be unaffected. So we are dealing with fluid that is overall neutral, right? So all of the charges in the fluid will add up to zero, but of course it has charged particles. It's overall neutral, and these charged particles, the distance scales is much smaller than the scales in which MHD is applied. Okay, so we cannot separate the different charges, and they are indistinguishable. So we overall see a neutral plasma. These are all the assumptions that I'm reviewing. Okay, all right. So one thing is that in any discussion of magnetohydrodynamics, the electric field is not given much importance. The reason being is that the fluid is considered to be infinitely conductive. If sigma of the fluid is infinite, right, what that results in is the electric field in the fluid to be zero. Why? Infinite conductivity of the material implies that the electrons, the free electrons, have infinite mobility. So they can immediately respond to any potential gradients developed in the medium. And if they can respond infinitely well, if they have infinite mobility, then there's no question of any non-zero potential gradient developing, because they'll immediately move to cancel out these potential gradients. The charges will immediately move in response to these potential gradients. And if there are no potential gradients in the medium, if the charges move to cancel these out, then there is no electric field in the medium. So an electric field cannot be sustained in that medium, and they vanish. In the fluid frame, this is for an observer in the fluid frame. Now we'll ask the question that, okay, what about an observer in the lab frame? If the fluid is moving with respect to the if in the lab frame with some velocity v, then what is the electric field that this observer will see? Okay, and we'll work with plasma that is isotropic. So technically, the sigma could have been a matrix because you have a vector on the left and right hand sides. You could have a tensor over here, but we assume that the off-diagonal elements of this tensor vanish and that the diagonal elements are all the same. So this is just a scalar. What it means to say that the diagonal elements are the same is that plasma is isotropic. The response of the material, which is the current, to an applied electric field is the same along all directions. Okay, Jx, Jy, Jz will be the same, given by the same sigma, Ex, Ey multiplied to Ex, Ey, Ez. All right. Okay. So now we want to ask the question, what about the electric and magnetic fields that a lab observer will report about this fluid? Okay. This fluid which is immersed in some magnetic field, what will a lab observer report about the electric and magnetic field of this fluid in this medium? Okay. All right. So we look at the Maxwell's equations. Okay. These are dynamical equations. These are constraint equations. And we know that the fluid has zero electric field. We want to ask the question, what is the electric field in the lab frame? To do that, of course, there's a frame transformation involved. Why? Because let's say this is the frame of the lab, and the fluid moves with respect to the lab frame in this direction, denoted by this red arrow. But to the lab, so what does the lab do? It moves with velocity v with respect to the fluid in the right in the right direction, right? So there's a frame transformation involved. If you know the electric field in the fluid, now you want to ask the question, what is the electric field in the lab? And so there's Lorentz transformation involved, because now you're moving to a boosted frame. You're moving to a frame with respect to the fluid. You're moving to a frame which is moving with respect to velocity v. Okay, so there's Lorentz transformation involved. How do you know the transformation? Well, this is the transformation. The electric and magnetic fields are all part. So these are details that you can skip for now. I'm just telling you where are the equations relating these electric and magnetic fields in these two frames coming from. These details are not part of your syllabus. I'm just trying to tell you where these come from. Okay. I'm not going to go into the details either. I'm just telling you where they come from. So FPNU is a field strength tensor. It is given by this. You can see that this depends on Ex, Ey, Ez and the XYZ components of the magnetic fields. It's an antisymmetric tensor, which means that if you invert this nu mu, you get a minus sign. So these components are set by demanding that if you take the transpose of this, you should have a negative sign over here. So they come with basically plus signs over here. Okay. Lambda is a Lorentz transformation matrix. And for the transformation that gives you a boost along x direction, this looks like this. This matrix looks like this, where you have 0, 0, 0, 0 over here, also here, and this is a 2 cross 2 identity matrix. This is the matrix corresponding to the boost along x direction. And if we know acts like a tensor, transforms like a tensor, it's a tensor. So you'll have two matrices multiplied to this. If you take care of this, if you're careful with the multiplication, you will see that the components give you these transformation laws, which were written in the lectures. Okay. Once again, remember the primed variables are the quantities in the fluid frame. The unprimed variables are quantities in the lab frame. Okay. So you have related E parallel, which is parallel just means the component of electric or magnetic field parallel to the velocity of the frame. Perpendicular means any direction perpendicular to this V. Where V is being taken along x direction in this case. Okay. So we have related the electric and magnetic fields, the components of electric and magnetic fields parallel to V in the two frames as well as the perpendicular components. Okay. But we know that E fluid is zero, which means that E parallel prime and E perpendicular prime are both zero. What we can say from these two equations is that E parallel is zero, which means that the electric field parallel to x direction, electric field along x direction in the lap frame is zero. This is what this tells you. And what does this equation tell you? If the left hand side is zero, then you can relate E perpendicular to minus V cross B by C. This tells you that the electric field in the YZ direction in the lap frame is related to the magnetic field in the lap frame via this equation. So what you have done is you have expressed for an infinitely conducting fluid the electric and magnetic field in the lap frame. Remember, once again, this is for an infinitely conducting fluid, for which you can claim that E fluid is zero. The electric field in the fluid frame is zero. Okay. And if the fluid moves non-relativistically, then this factor V by C, where remember V is the velocity of the fluid, velocity with which the fluid flows, then this factor of V by C, if the fluid is non-relativistic, then V by C is small, and you can ignore E perpendicular with respect to B. Then we say that even in the lap frame, the electric field of the fluid is small. Not zero, small. Okay. Is this clear?
Yes.
Okay. All right. So this is a very important relation. What we can do this with this is that we can use this relation in one of the Maxwell's equation and get an equation which tells you which is completely in which is completely in the variables of the magnetic field, right? So you can substitute for E over here, and this will give you a minus 1 by C curl of V cross B, and you have a minus 1 by C del V del T on the right hand side. Minus 1 by C cancels to give you a del V del T equals curl of V cross B. This tells you the dynamics of the magnetic field in the lap frame, the relation of the how the dynamics depends on the existent magnetic field and the fluid profile, the flow profile. And it's very important because now you know you can ignore E and you know everything about the B dynamics. This is the induction equation. Okay. But once again, we derived this equation for an infinitely conducting fluid. You can take into account corrections coming from finite conductivity, but the conductivity is not infinite. If the conductivity is not infinite, you can write what happens is you have to add a term which is lambda Laplacian of D, where lambda is related to the conductivity, and lambda goes to zero. This term goes to zero if your conductivity goes to infinity, right? What this term essentially is a dissipation term. It tells you how the B field will decay in the fluid. which is now finitely conducting, which is not infinitely conducting. So you know that a B field will decay in a finitely conducting medium. Okay. Why is that? Because recall there was something called a Reynolds number that was the ratio of the inertial term to the viscous term, which has dimensions of velocity times length scale divided by nu, where nu is the coefficient of viscosity. That is exactly what you get if you take the ratio of these two terms. This is the proxy for the inertial term. This is the proxy for the viscous term. That gives you the magnetic Reynolds number. This is also something that was discussed when we discussed Mach numbers, Reynolds numbers, magnetic Reynolds numbers in week 2 or 3. This is the magnetic Reynolds number. And lambda is something called the magnetic diffusivity. Diffusivity, if I'm pronouncing it correctly. Yeah. So this term tells you how the magnetic flux is dissipated in a finitely conducting medium. Okay. And if you ignore this term, if you find out the solution of the equation del B del T equals to lambda elliptation of B, which is like a diffusion equation, you will see the solution is actually this. If you start out with a delta function pulse for the B field, that this will broaden in time and the height will decay. The height will reduce. So this profile will broaden and decay with time. So you have dissipation of magnetic flux in the fluid for finite conductivity. For infinite conductivity, this is what tells you the dynamics of the magnetic field in the fluid.
So is the induction equation the analog of the Navier-Stokes equation here?
Navier-Stokes equation has so this is the induction equation. Now, if you account for finite conductivity, I should probably not call this induction equation, but yeah, induction equation with finite conductivity. You are right. This is
Okay.
the analog of Navier-Stokes equation. Right. Good. Okay. Okay. Let's conclude a few more things from this topic. Uh, so let's once again use this relation that we got from frame transformations, the way we related the electric field and magnetic field uh, of the fluid in the lab frame. Let's use this relation in the second dynamical Maxwell equation, uh, and let's substitute the value of the expression for E in this del E del T. What that gives you is curl of B equals to 4 pi J by C minus del del T of V cross B by C square. Okay. Now, if you are dealing with a non-relativistic fluid, you can ignore V by C square. V by C square is very small, so you can ignore this term, right? And then you're left with curl of B equals to 4 pi J by C. Then you take divergence on both sides. Divergence of curl is 0, so you're left with divergence of J equals 0. And divergence of J equals 0 tells you that there are no sources or sinks in the fluid. In the MHD treatment, there are no sources or sinks. Divergence of J is 0. Okay. Another important thing is you look at the induction equation with infinite conducting fluid. This is the induction equation. If you take divergence in both hand sides, we know that divergence of curl is 0, so this right hand side goes to 0. And then you have del del T, divergence of B equals to 0. Nowhere in the image treatment are we feeding the information that divergence of B is equals to 0. Okay, we don't feed in the information that there are no magnetic monopoles. We say that divergence of we have never said that divergence of B is 0, but the induction equation is spitting back this. It's giving us back this thing, which tells us that it doesn't tell us that divergence of B is 0, but rather it tells us that whatever divergence of B you start with, whatever initial condition you start with, that is conserved along the that's conserved with time. So divergence of B stays the same. Okay. Of course, divergence of B is 0. We know that. But induction equation, even without providing this information, induction equation tells us that whatever divergence of B you start with, that's conserved with time. All right. Any questions? Okay, so let's start with the sample assignment problems. Uh, look at this image. You can see these V-shaped structures. This isn't supersonic aircraft, right? We have to pick the correct options. An observer will hear a sonic boom just when the V-shaped structure passes him or her.
I think it will be false because there's something of causality here.
No. So these, what are these actually? What are these V-shaped structures?
The shocks.
Absolutely. When would you hear a shock?
Uh,
Okay, so contrast option A with option B. B tells you that an observer will hear this sonic boom much before this structure reaches him or her. Now that is something that will violate causality, right? This, what is the sonic boom? You hear these shocks. When these shocks pass you, that is the sonic boom, right?
okay.
Right?
Okay.
It's a
Okay.
huge pressure discontinuities. Within a very small region, there's a huge pressure jump, right? That's what creates the sonic boom. So you will actually hear this when the V-shaped structure passes you. You can't hear this before it passes you. This is the sonic boom.
Okay.
Option C, there will be no sonic boom.
False.
False. There is a sonic boom. We know that. We hear it when it passes through us. Hmm? The V-shaped structure represents a shock.
True.
Correct. Correct. The correct options are A and D. Okay, we'll move on to the next question then. Alright. This is, once again, this image was shown in the class. This is radio emission from a supernova shell, right? Uh, the red parts are the most intense radio waves, and as the color fades from yellow to green to blue, the intensity falls, and we have to choose the correct statements. Um, A and B tell you, A tells you that the particle density in the red regions should be lower as compared to the blue regions. B tells you particle density in red regions should be higher as compared to the blue regions.
B should be correct because the shock actually carries the particles along with. I mean, it snowplows the particle along with it.
Absolutely. Absolutely. Understand that this is something that we expect to be the shock front. This is the shock shell that's moving out. All of these things have been shocked at an earlier time, right? So, if you remember, we converted to dimensionless variables, and I told you that the solutions they're also plotted in the class. Well, this is what the solution looks like. Okay, this is zeta by zeta naught, where zeta naught is this axis is zeta by zeta naught, where zeta naught is the position of the shock shell. So zeta, when zeta is equals to zeta naught, this is where the shock shell is at this zeta. Remember, zeta is a combination of R and T. So you can't say that this is the radial position. It's a combination of R and T. Okay. However, we do know that as we go to smaller zetas, we are moving to inner regions of this sphere. It's a combination of R and T, but these are still similar solutions. We know that as time progresses, the shell has moved outwards. So of course, as we move to smaller zeta, we are going to move to inner regions. Doesn't scale directly, but we know that as we move to smaller zeta, we move to inner regions of this sphere. Okay, and the y-axis gives you velocity, density, and pressure. Okay, so now this will help us choose the correct solution. Uh, Option A and B told you that the red regions densities were lower or higher in compared to blue. So we can see that as you move closer to the shock shell, the density rises. So of course, the particle density in the red areas would be higher in comparison to the blue. Or as Aniket pointed out, it is true that as the shock plows through the interstellar medium, as it plows through the ambient space, it corrects particle, right? The particle density should uh, rise as you move, as the shock front moves outwards. That's correct. So B is indeed correct. Okay. All right. The roughly spherical structure is probably a shock that accelerates particles. That is something we, as from our, if this is of course correct, then the correct way, of course, to look at this picture is that the spherical structure is indeed a shock that accelerates particles. So C is correct. The gas in the red areas is relatively cooler in comparison to the gas in blue areas.
No, because it's a radio image.
Absolutely, absolutely. Another way to say this is that, of course, the temperature will scale as the pressure. Pressure and temperature are proxy for each other, and you can see that the pressure will rise as you go closer to the shock front. So of course this will rise, and clearly it's a radio image. It's this tells you the radio, and the more intense region will of course will be hotter. So this is wrong. So the correct options are B and C. Okay. Uh, Consider a spherical blast wave, and it obeys. So we never named it in the lecture. These are Sidhu-Taylor solutions. These are self-similar solutions, right? We have discussed a bunch of approximations when we studied these blast waves. Now we have to pick the correct statement. Consider two time instances, T1 and T2. T2 is a latter instant of time. Now you have a bunch of options. We have to choose the correct one, which tells you that the energy contained in the blast wave at T2 is greater than that at T1. The energy contained at T2 is lesser than that at T1. The energy contained at T2 is equal to that at T1, and the energy contained oscillates up and down.
I think it should be C because there is no dissipation assumed.
Absolutely, absolutely. Remember that we said that this blast wave was a result of um, energy deposition, and a certain amount of energy deposition at a point. This energy goes into the shock waves and it propagates, and the a crucial assumption was that this does not dissipate, right? So in these solutions, in these types of solutions, the energy does not dissipate. So at different times, the energy contained in the blast wave has to be the same. So the correct option is C. Okay, now we have to choose the correct option. This talks about the scales at which MHD is applicable, and it compares the MHD length scale. Okay, now MHD is applicable for length scales much smaller than the charge separation length scale, or it deals with length scales much larger than the charge separation length scale.
B.
Absolutely. We just discussed that one of the assumptions of MHD is that we will not be able to distinguish the different charges from each other. The plasma will overall look neutral, but we won't be able to distinguish different particles from each other. We are still working in the fluid approximation. So B. Okay. C and D. MHD is applicable for frequencies much lower than or much higher than the plasma frequency.
C.
Much lower than the plasma frequency. Now, why is that? Plasma oscillations were discussed in the lectures, right? To observe plasma oscillations, you would have to observe these electron layers of electron oscillation about their equilibrium position, right? Now, this occurs at a certain frequency. This takes a certain time to oscillate. We have to operate at frequencies. We are actually operating at frequencies that cannot resolve these time scales. Okay, so we are working with frequencies much larger. We're working at time scales. We are working with frequencies much smaller than these frequencies, the frequency of oscillation of these plasma. So we're working with time scales that cannot resolve, because they're much larger, they cannot resolve the time scales of these electron oscillations, right? So MHD is applicable for frequencies much lower than the plasma frequency. The correct option is B and C. Okay, all right. Last question. Consider the MHD induction equation with a dissipation term. Eta is the magnetic diffusivity. Now we have to pick the correct statements. The first term on the right hand side governs the decay of B.
False.
The second term on the right hand side governs the decay of B.
True.
True. Eta is a magnetic diffusivity. We just discussed the significance of this term. Okay, so B is correct. The first term on the right hand side is more important at low magnetic Reynolds number versus the first term is important at high magnetic Reynolds number.
D.
D. Absolutely. Why is that? Because remember, Reynolds number was the ratio of in the normal fluid without let's say the usual Reynolds number, not the magnetic Reynolds number. If you ever forget which term is important as opposed to what, remember that the Reynolds number the usual Reynolds number, not the magnetic one, was the inertial term by the viscous term. The viscous term is the dissipative term. Over here, the analog of this viscous term is this diffusion term, right? So the magnetic Reynolds number is actually the ratio of this divided by this. And when is this ratio high? When this is large. So this is important. We can ignore this. This is the dominant term when the Reynolds number is high, when the numerator is larger than the denominator. So the first term is more important at high magnetic Reynolds number. So the correct option is B and D. That's it. That is all I wanted to discuss today. If you have any questions, you can ask. Also, Shreya, I'm not sure if you watched last week's recording. I said it towards the end. You had unfortunately left. The exam is going to be MCQ pattern. I spoke to the coordinator.
Thank you, ma'am.
Okay. So that's that. If you have no questions, you can leave and I can end the recording now.